Hello everybody and welcome to today's video on rates of change. We're continuing chapter 1 of calculus and vectors. Today we're going to learn a brand new topic, and that is limits. Limits are one of the fundamental concepts for calculus, so it's really important that you learn this concept well. So today we're going to actually talk about what a limit is and how we can apply it for different situations. So what is a limit? Well, a limit is the value that a function approaches as the input approaches some value. So essentially, if we are approaching the number 2, our limit would be the value of f of x at that point. Of course, it gets a little bit more in depth than that, but if that helps you remember it, then that should be good. So a limit only occurs when 3 key conditions are met, and these are the following. So here, this is how you write what a limit is. So limit of f of x needs to exist when x is approaching some number from the left-hand side. That's what the negative sign means. So if we were talking about 2, if we wanted to talk about as x approaches 2 from the left-hand side, we would write x with an arrow, 2, and then a little minus at the top. So that value must exist. The value also must exist when we're approaching a number from the right-hand side. So if it's from the right, it's a plus. If it's from the left, it's a negative. Now, the most important part is that if both the limits do exist, they must also equal the exact same thing. So if you got 2 for your right hand limit and your left hand limit got us 3, that means the limit does not exist. Limits are extremely useful when it comes to analyzing different functions. For example, a sequence. A sequence is a type of function which is denoted by this here. So f of n is equals to t with the base b, whose domain is a set of natural numbers. So that might sound a little bit confusing, but a sequence is essentially a nice pattern. So for example, if we're talking about the pattern of, for example, n squared minus n, that sequence can be analyzed using limits. Limits are also extremely useful when it comes to dealing with continuous and discontinuous functions. Those two words are probably new to you, which is why I've explained what they mean here, but essentially a continuous function is a function where x, or the graph, is always continuous and always is defined, such that x is a real number. Informally, so if you don't think about it in mathematical terms, all that means is that if we had the function, we could write it or draw it with a single stroke. There's no need for you to pick up your pen and then place another point. However, a discontinuous function would have gaps, or for example, holes that you have to skip in order to draw it. So if there was a hole over here, you would have to lift your pen, right? Otherwise, you would draw it as though there is a value. So of course, thinking of these two ways will help you figure out if a function is continuous or discontinuous. We will actually go over those two graphs more in depth in the next chapter. However, hopefully that got you a quick little overview of what a limit is. So now let's talk about the application of a limit. So for example, let's learn to apply limits to analyze the end behavior of a sequence. So you could either just analyze the limit of, for example, this sequence here, so n to the power of 3 minus n squared, and find the limit at a particular value, or of course you could use limits to figure out the end behavior. So let's analyze it in this case. So if we want to find its limit for any of the terms, we can start doing this by calculating a few terms first. So you would plug in 0 here, so 0 to the power of 3 minus 0 to the power of 2 is 0. If you plug in 1, we have 1 to the power of 3 minus 1 to the power of 2, which is still 0. If we plug in 2, we get 8 minus 4, which is 4. If we plug in 3, that'd be 27 minus 9, which is 18. And we would go on and on and on until we're satisfied with the number of terms we have. Of course, even by looking at the ones we got so far, so 0, 0, 4, and 18, we already see that the numbers are beginning to grow. If you want to find a pattern rule for that, it probably would be a little bit difficult, but because it's already given to you. But essentially, if you keep growing those numbers, you'll actually see that they are diverging, that they're not going to the same value. It seems like they're spreading further and further apart. That is a key feature that you must recognize, because if that is occurring, that means you don't have a limit. Again, remember, a limit only occurs when all numbers approach the same value. So in our case, since they are all diverging, so they're approaching, like they're getting further and further apart, we can't possibly get towards a singular value. However, what we can see is the fact that as they grow further apart, so as the more x's we have, as the more values we calculate, the greater they become. So we can actually see that they are approaching infinity as x grows bigger. So this is what we used to think about when we were talking about end behavior. Remember, if it went from quadrant 3 to quadrant 1, we would say it goes from negative infinity to positive infinity. So now we can actually describe it in a more precise way by talking about its limit. Since we've discovered that this particular sequence is moving from 0 to positive infinity, it's going like this, that means we can actually express its end behavior by its limit, which we can write like this. So over here, we actually have the limit of our sequence, which was here, and then we express as x approaches infinity. Again, this is just one of its end behaviors. Remember, if you were going to negative infinity, we could also try to find what happens there. But just making this simple, as x approaches infinity, the limit of this sequence is equals to infinity. Again, the equals might be a little bit confusing because we don't actually reach infinity, we're approaching it. And thus, technically we shouldn't have an equal sign, but that is how we write these limits, and so that is the proper convention. Another thing that you must be able to do is, of course, analyze a graph and be able to evaluate the limits at certain points on it. Of course, the reason why you would want to do this is that later on, you'd actually need limits in order to understand what a graph is doing. For now, we've learned functions and advanced functions, so we're kind of familiar with like 5 key functions. But if we started mixing them together and asking you about its behavior, you might not know enough about those functions, and that is when limits come in. Of course, since we don't know how to do that yet and we haven't practiced enough with limits, I'd actually like for us to just evaluate limits from a graph, which is why I'd like us to look at question 13 in the textbook. So here is question 13, and it asks us to examine the given graph. So immediately by looking at this, for given the function, it is a polynomial with a degree of 3, we have a negative, so we can talk about its reflections and its different transformations, but the question asks us to state its domain. Again, the way we know to do it right now is to figure out where is x defined. Well, it's defined everywhere because it is a polynomial function, and so the domain of this function is that x is an element of all real numbers. Now, it's asking us to evaluate the limits. So let's see here. We have the limit of our function as x approaches -2 from the left. So where is -2? Well, -2 is over here, so if we are approaching it from the left, we're going to be coming to this point, which appears to be 0. And so our answer would be 0. If we were to look at the limit from the right-hand side, it would be coming from this way, and again, we see that it approaches 0. And so the limit, again, is 0. Now it's asking us what the limit is at -2. Well, we know that if the limits at the left-hand side equal to the right-hand side, that means that the limit at that point would be equivalent to these two. And since we got the same number, that would mean that the limit as x approaches -2 is 0. Lastly, our question asks us what is f of -2 equals to. And of course, we just find where -2 is located and we find out that is 0. So what we just learned is that if the limit is the same from the right-hand side and the left-hand side, it seems that the limit of that value is the same as the actual value for that function. So if we, for example, tried this out for a different point, for example, let's look at 1. So it seems like at 1, we have the value of 3. So if we went to 3 from the left-hand side, so from here, we seem to be approaching 3. If we went from the right-hand side, again, it seems like we're approaching 3, and thus the limit as x approaches 1 is equals to 3. This type of behavior actually tells us that the graph is indeed continuous, because the definition for a continuous graph is that if the limit of that value equals to the value of f of that current position, it is continuous. So again, we tried at -2, they were the same. We tried at 1, they were the same, and thus we can prove that the graph is continuous. If we were to see a point where the limit does not equal to the value of the function, that would prove that the graph is discontinuous. So for example, if we put a hole let's put a hole over here, right? The limit would exist because we're approaching what it seems like as 4 from both top and bottom, so from both left and right. However, since it is a hole, the function is not defined at that point, and thus the graph is discontinuous. Hopefully hearing and listening and doing that little example has let you understand more in depth what a limit is and how to use them. But in case you still want extra practice or just want to solidify your understanding, I've actually assigned the following questions. Questions 1 to 6, 1 to 8 that I've listed here are all very, very similar. They require you to understand the basics of what a limit is, and they just let you practice. I'd say questions 10 and 17 might be a little bit difficult. 10 would just require you to think a little bit outside the box, but I'm pretty sure most of you will get that answer like really, really quickly. 17 might seem difficult, but I assure you it is not. In case you were wondering what question 17 is, here it is. It's asking you to just construct a table of values to determine these limits here. The reason why you need a table of values is so that you could plug in values that are very close to -2 from the left-hand side and very close to -2 from the right-hand side. So for example, -2.001 and -1.999. Those are two values that would satisfy 1 and 2. Also, if you really, really, really want to learn more, I'd really suggest doing question 15. As you can see, it is half the page, but it's pretty fun. Like, all you have to do is also fill out this chart. then you have to understand what the values are approaching. This number you might have heard of, you might have not, which is why I didn't assign it. But in case you really want to try it and just give it a shot, I'd really encourage it. If you want me to solve it, I'll happily do it. Just leave a comment down below. But yeah, if you want to do these questions, I'd really encourage that. So again, I'd like to thank anybody who has gotten this far in the video. You guys are truly amazing and I admire your dedication to your studies. I'm gonna try to upload more this week, so that is I guess this is the final week of November, or the final whole week of November, because I'm finally starting my second quad. But either way, I should finish all of the videos by the end of January. I'm gonna take all of the winter break to do these for you guys, so you guys are well prepared for when calculus and vectors actually starts. So I can't wait to do that. Again, thank you so much for listening, and I hope to see you next time. Bye bye!